So now that we've taken a look at these functions on that little applet, let's try some of these investigation questions. So this is now at the top of page 16 in your booklets. And we're just going to fill out values for sine theta as theta moves through a number of different degrees. And while I'm doing this, I'm trying to think of that unit circle, and for sine theta, I'm thinking about what the y-coordinate is at different positions. Negative 90 degrees, if you imagine the unit circle a bit like a clock face, that's at 6 o'clock. So I know that the y-coordinate would be negative 1 down there. 0 degrees is back at my positive x-axis, the y-coordinate is 0. And now I'm just picturing moving around that circle anti-clockwise. So 90 degrees will be 1, 180 will be back down to 0, negative 1, 0. 450 degrees, we're just moving on an extra 90 degrees, so I'm back up at 12 o'clock if you're thinking about that clock face. Okay, so we can see the greatest value of sine theta we're ever going to have is 1, and the lowest is negative 1. Okay, doing the same for cosine. So I'm looking at my x coordinate now. So I'm starting at 6 o'clock, so that is x coordinate 0. Then on the x-axis, positive x-axis here, so it's 1. And then I'm just going to keep going round now. Okay, and then we can obviously plot these. So I'm going to do my best to plot these on here. So these are the points for the sine curve I'm going to try to join up. This is going to be a little bit tricky. Let's see. Okay, so you see I'm doing my best to not just use straight lines. I'm trying to use a smooth curve. So that one is y equals sine theta, or I guess sine x here. Let's use a different colour for cos. So cos starts at 1, so I'll go up to 1. There we go, y equals cos theta. Okay, a few things that we should talk about. Obviously, these are periodic. The period is 360 degrees. The amplitude is the height from if we imagine a line that they're oscillating around, that they're going above and below, we call that line, here it's the x-axis, but we call it the principal axis. Principal axis. So for example, if we translated this up or down, we could still find a principal axis that they're oscillating around. We have an amplitude for both of these, that's the height from the principal axis up to a maximum or down to a minimum. The amplitude is 1. For our cosine graph, an important point is where it crosses the y-axis, its y-intercept, which is at 0, 1. For the sine curve, it goes through the origin, so it's 0, 0. Okay, differences between these. The cosine curve is an even function. It is symmetrical about the y-axis. The sine function is an odd function, and we'll talk a little bit about that on question 11 down here. Okay, let's take a quick look at drawing these on our calculators, set first in degrees and radians, and just see how they differ. So I am in, let's make sure I'm in degrees. Okay, and I'm going to type in sine x. Okay, I can't scroll very nicely on this version, so I'm just going to put in, maybe I'll set it the same as the graph above, so, oops, I've done it again, negative, oh my goodness, this isn't going very well, is it? I need to use the negative symbol, that's why. And let's go up to 450, I don't really need to go quite that far. Let's go down to negative 2. Oh, okay, negative 3 it is. Well, let's make it positive 3 as well. Okay, so there is my function, my sine curve. Now let's look at what happens when I change into radians. So, not changing the function, I'm not changing the window. Let's just check that's still set up as I almost intended. And let's go to the graph. Okay, a mess. What's going on? Obviously, it's down to the measure that we're using for our angles. So when I was using degrees, it takes 360 degrees to complete a full period or full wavelength. When we're in radians, a full circle is 2 pi, which is 2 lots of roughly 3.14. So that means it's taking about 6.28 to complete a full rotation. So I've got many, many rotations or many, many wavelengths happening here. So let's change my range now. Let's go from negative pi. Well, let's do it the same as it was, negative pi by 2. And we had 450 degrees. So I'll go up to, should we go up to 2 pi? It's taking up to 300, the equivalent of 360 degrees. Okay, and that looks a bit more like we were expecting. So obviously, changing between radians and degrees affects the wavelength. It doesn't affect the amplitude. It was still going through the origin, but it is affecting how long a wavelength is. So we obviously need to be a little bit careful when we're using our calculators to answer problems. Okay, so let's move on to question 10. We'll stick in radians as that's what we are in. Let's do the graph of sine squared x. So I'm going to put that in brackets, sine x, and then I'm going to go out to square it, plus cos x, out there. Okay, let's take a look at this one. Oh, okay, a straight line. Let's see, does it change if I'm in degrees? It shouldn't really, and no it doesn't. A straight line at 1. Okay, so we get the line y equals 1. Let's go back to our unit circle and think about why that's happening. So if we look at, if we remember, so we're talking about sine squared x plus cos squared x. Now, we said that sine x was our y value. You'll notice we're treating x and theta quite interchangeably because we're switching between diagrams with theta and our calculator, which is in terms of x. And then cos was our x coordinate, so let's change that to x. So in my diagram, sine squared x plus cos squared x is equivalent to this. And then if we look at this, we've got a right angled triangle, and we know that if we have the sum of the squares of the shorter sides, we get the square of the longer side, the hypotenuse. This is Pythagoras' theorem, and of course that's going to be 1. So we get this as a result. Okay, it's one of our identities. Sine squared x plus cos squared x is always equal to 1. These are listed on page 16, so you don't need to worry about making a note about those. But that's how we could explain it using the unit circle. Okay, use the unit circle to explain why cos negative theta is equal to cos theta. Okay, so I've got theta here. Let's do my best to draw negative theta. If I drew negative theta perfectly, it would look like this, wouldn't it? And as we're talking about cos, we're talking about the x coordinates. And of course, the x coordinates are equal here. Okay, and as theta grows larger and negative theta grows larger, the x coordinates will stay lined up. So cos of negative theta is always equal to the cos of theta. And let's talk about sine. So I've still got theta and negative theta here. Now we're looking at a reflection, because if I'm talking about sine, I'm talking about the y position now. And the y position of this and the y position of this, it's as if they've been reflected over the x-axis. Okay, so the y coordinate will be the negative version of this y coordinate up here. And once again, as I move theta, as I make theta larger, negative theta becomes larger. They're still going to be symmetrical about the x-axis. So for that reason, the sine of negative theta is always equal to the negative of sine theta. And we can see that from the graphs as well. can see the symmetry with a cosine graph means that a positive value for our angle and a negative value for our angle, we're going to get the same output. And with our sine curve, this rotational symmetry about the origin means that if we have a positive angle and the opposite, they're going to be just the opposite outputs again. So this is summarised here. These are all the results we've come across. We started with this one from our unit circle, and we just looked at these other three now.